A system is stable if every bounded input yields a bounded output. For a system to be stable, the real parts of the poles of the closed-loop transfer function have to be negative. One of the techniques to analyze the stability of a system is Routh-Hurwitz Criterion. This is for LTI systems with a polynomial denominator. It determines if all the roots of a polynomial lie in the left half plane, that is, the real parts of the poles are negative. It also determines the number of roots in the right half plane. It does not explicitly compute the roots. The advantage is that higher order transfer functions can be handled by hand calculations. So the system with its characteristic polynomial d of s is stable if all the entries of the first column of root array are of a one sign. So we may construct root array as such, and we may calculate the other entries of root array using the following expressions. The number of sign changes in the first column of root array are equal to the number of roots in the right half plane. Now let's take a look at some examples. In this example, we see that all the entries of first column of root array are positive. So there is no sign change, that is no poles in the right half plane. So the system is stable. This is the next example. Here we encounter one of the two difficulties of Routh-Hurwitz Criterion. Here we see 0 in the first column of root array. In order to handle this, we replace 0 by a small positive epsilon. After such a replacement, we end up with two sign changes, that is, two poles to the right of the j omega axis. This means that the system is unstable. The second difficulty that we may encounter is zero-row issue. Briefly, we may say that when we encounter such difficulties, we can directly say that the system is unstable.